Hello everyone, I am Nandini MK studying in SVCE Bangalore. Today's subject is Theory of Computation. The topic is Turing machines, verifying whether one-tape Turing machines run in a linear time, verifying time complexity of a Turing machines. Now we have to know abstract. We discuss the following family of problems parameterized by integers. C is greater than or equal to 2 and D is greater than or equal to 1. Does a given one tape a Q state Turing machine make at a most Cn plus D steps on all computations on all inputs of a length n? For all n, assuming a fixed tape and input alphabet, we show that these problems are co-NP complete and we provide a good lower bounds. Especially, these problems cannot be solved in a O, Q of C minus 1 by 4, non-deterministic by time, multi-tape Turing machines. We also show the complements of this problem can be solved in a OQC plus 2, non-deterministic time and cannot be solved in a OQC minus 1 divided by 4, non-deterministic time by multi-tape Turing machines. Now we have to know introduction of a Turing machine. One of the goals of researching in the field of computational complexity is to understand computation better. While Turing machines are a basic model of a computation, we cannot algorithmically tell even whether a given Turing machine has an empty input. So we have to ask simpler question or use a simpler model to analyze. Assume we have a fixed function t is to n r is greater than 0. A natural question to ask whether a given Turing machine runs in a time t of n. Does a given Turing machine make at a most t of n steps on all computations on inputs of a length n for all n? Note that there is a no big OH notation in the question. The reason for this, the flow folkloric result that is the undecidable even whether a given one tape Turing machine runs in a time O is to 1. Furthermore, it was proven in 6 that the aforementioned problem is not decidable. For linear function, T we allow a multiple tape Turing machines as a input. On the other hand, we restrict the input to 1 to tape, Turing machines can take a each CD implies n. We get a z decide to given a non-deterministic one tape Turing machine in a time to C of n plus d. We name this problem we have to turning machine. There exist different notations of a running time for non-deterministic Turing machines in the literature. However, in this work, the length of a longest computation on an input takes as a measure for the time needed of a hearts and that input. We will also consider problems D hearts Cn plus D, which are analogs of a problems heart Cn plus D for a non-deterministic or deterministic one-tape Turing machines as an input. While one-tape Turing machines can solve the same problems as a multi-tape Turing machines, they are a bit solver, however, a bit simpler to analyze. It is well known that one can simulate a multi-tape Turing machines that runs in a time t of n with a one-tape Turing machine that runs in a time O of t of n by 2 and that quadratic slowdown is a inherent aid. On the other hand, a thing that makes the analyze the of one tape Turing machine simpler or crossing a sequences. They were first studied in the 1960s by Haney and who proved one of the most well-known properties of the one-tape linear deterministic Turing machines. They recognize only regular languages. Harmonies extend this result to one-tape deterministic Turing machines that run in a time O n log n, and it was a furthermore extend to non-deterministic Turing Machines by Kobayashi and Tadakai Yamakami and Lin. If we would take a different definition of a running time of a non-deterministic Turing machines, such as a considering only a shortest accepting computation, then linear time, one-tape non-deterministic Turing machines would be able to accept also non-regular and even NP complete languages. We do not consider such machines in carrying a summary of a result about the one tape linear time Turing machines offer different tapes. The next is methodology. Define the problem. Specify the input size n of n, example, length of the input strength. Clarify what it means to run in a linear time. That is, the machine's number of steps should grow up proportionally to n. Tape movement count. Track how the tape head moves across the input tape. In a linear time Turing machines, the tape head should make no more than O of n moves. State transitions. Examine the transition function. The machine should not ever circle or state that would cause it to revisit a tape location more than a constant number of times. The next is analysis of a loops. If the turning machine has a loops, for example, when checking multiple characters, verifying that they iterate only a constant number of times for each input character, contributing to the overall of a O of n steps. Function count. Check the treatment of a function that are called repeating of should be complete. It's a task within at a turning machine. The next step is simulate the machine. Run the machine on a several input strings of a increasing sizes. Count that number of a transition and verifying that it grows linearly with the respect to the input size. The next is estimate upper bound. Determine an upper bound on the number of a transition based on the structure of the Turing machine. Ensure that the bound is C of n, where C of C is constant. The next is Turing machine basics. A step tape. Turing machine uses a single tape and a head to read or write symbols based on the machine state transition. The next is linear time definitions. Running in a linear time means the machine's finishes computation in a O of n steps, where n is the size of an input. The next is one tape challenge. The machine has to move left or right after each step, making it less efficient than multi-tape machines for some problems. Key verification. To verify linear time, count the number of transitions the machine performs relative to the input size. The next is directed read. If the machine processes each symbol is constant time, scanning the tape in a one pass without needing to revisit symbol, it can run in a O of n time. The another one is avoid the excessive moves. If the machine frequently moves back and forth along the tape, it could increase the number of steps, leading to time complexity worse and then O of n. The next is worst case analysis. Check whether worst case input pattern causes of revisit early symbol multiple times potentially exceeding of on a n of steps. The next and last is state transition. Ensure that the number of a state transition grows of the without requiring non-linear processing for a symbol. This is the simple of problems. For straightforward tasks like a copying or simple decision problems, a one-tape machine can often achieve a linear time. The next is complex problems. For more complex computations, that one-tape machine may require non-linear time due to limitations in accessing different parts of the tape efficiently. The next is simulations of the Turing machine. Simulating the machine on different input size provides a empirical evidence of its time complexity. The next is head movements. Excessive tape head movements, particularly revisiting portions of the tape, can indicate a non-linear time behavior. The next is function of input size. The number of a steps should be a linear function of the input size to confirm O of n performance. This is memory of a usage. Though irre- irrelevant to time complexity, consider how efficiently the machine uses its single tape for a space as well. The last is optimization. A one tape machine can be optimized for a linear search scenario, such as a left to right passing without a backtracking. The conclusion for the Turing machine is verifying linear times requires that the machine processes each input symbol efficiently without unnecessary revisit or excessive tape movements, ensuring the number of steps grows proportionally to input size. Thank